Well, like many topics in engineering, antennas and radiation starts out really theoretical and then gradually becomes more applied. And I hope you appreciate that. We have to pay the price to get the theory, and then we can use that for all sorts of things, hundreds of applications, far more than we could cover in a one semester class. So, what we're going to do is take the far field radiation that we found from an antenna, that will be E, and sometimes we'll put an FF here for far field, or sometimes we leave that off. We take the electric field and we want to use that to find out things about the antenna. How does it perform and what does it do? Well, the first thing we do is we take that E and we get the um, time average power density. And for any antenna, that will have an R hat, some constant, which we sometimes call S naught. There's always an R squared down here. And then there's some function of theta and phi. And we can get that from the electric field using E far field magnitude squared for 2 eta r hat. That's a very similar formula to what we saw with plane waves. Okay, so we've got the far electric field. Our first step is to find the time average radiated power density, and the units there will be watts per meter squared as before. Okay, once we have the time average radiated power density, we can start to do things with that. And the first thing we'll look at is the radiation pattern. Radiation pattern really is this function of theta and phi. We want to isolate that somehow, and here's how we're going to do that. I'm going to use big F of theta and phi just to represent the fact that the normalization or the scale factor might be a little bit different than that little f. The radiation pattern is defined to be the S radiated by the antenna divided by S max. Now, this might not be obvious, but both S and its maximum value have a 1 over r squared in it. So the 1 over r squared that's sort of in the numerator and in the denominator, those will cancel. And all that's left is a function of angle, theta and phi. That's why we call it a pattern. It's where does the energy go in terms of angle? Does it go in a very narrow range for a highly directive antenna or a broad range of angles that we'd get for a small antenna? The radiation pattern governs where the energy goes. Now, once we have the radiation pattern, we can do a lot of things with that. We can plot the pattern. Now, really, the pattern is kind of a three-dimensional thing. For the Hertzian dipole antenna, the pattern actually sort of comes out radially. And the pattern is sine squared theta. So no energy goes up, and all the energy sort of goes out to the sides of the antenna. That's one particular radiation pattern. If we have a more complicated antenna, that three-dimensional plot is really hard to render, so a lot of times we'll do a cut. So I might just do a polar plot in the YZ plane, let's say. Now this is for a different antenna. Let's say we have a strong main lobe in this direction and some side lobes, and so on and so forth. Now in some directions, no field is radiated, and we call that a null. So the Hertzian dipole has nulls in the plus and minus z direction, or the theta equals 0, theta equal pi directions. A more complicated antenna could have many nulls. The largest peak, we call that the main beam. And a lot of times we're concerned with the width of the main beam, and there's kind of two ways to do that. Now, what I've drawn is a polar plot, kind of an ugly polar plot. If we want to be quantitative about it, what we might do is do a rectangular plot over theta, and that's called a theta cut or an elevation pattern. Now, I'm trying to translate the upper picture to the lower one, but in theta that might have a little side lobe, a bigger main lobe, and then some smaller side lobes going out from 0 to pi. Okay, now what's the width of the main beam? This is on a logarithmic scale, we can go down to the minus 3 dB points or the half power points, and that angular range is the half power beam width. Now sometimes it's a little more convenient to use the nulls. We can also have the null beam width. Okay? All right, so I'm just trying to introduce some terminology that helps us understand properties of the radiation pattern. I can also do a phi cut. I don't know what that would look like. Maybe it looks like that. That's a function of phi from 0 to 2 pi. Okay. Antennas also have an E plane and an H plane. If I have an antenna it goes in this direction, the electric field might be this way, and the magnetic field might be out of the plane. So if I plot the pattern along a cut in the plane of the screen, that's an E-plane cut of the pattern. If I go orthogonal to the screen in the direction of the magnetic field, that we call the H-plane. And really all of these cuts, E-plane and H-plane, theta cut and phi cut, are really just ways to transform a kind of a complicated 3D plot into something that's two-dimensional and a little easier to get a handle on. But sometimes we'll actually plot the radiation pattern in 3D using color or graphical rendering and things like that. Okay, now a little bit more terminology before we leave radiation pattern. If the radiation pattern is the same for all angles phi, in other words, no azimuthal variation, we call that an omnidirectional pattern. It doesn't mean it can't vary in elevation. We might have no radiation in the vertical direction. So a Hertzian dipole in the z direction is omnidirectional. So the power goes out equally in all directions horizontally, but maybe less in the vertical direction. Now there's another pattern which is entirely idealized. No antenna has this radiation pattern, but it's important as a reference, as we'll see in just a minute, and that's the isotropic antenna. And this is ideal. It doesn't exist, but it's sort of an idealized reference. So there's some terminology for radiation patterns. Now we'll try and be a little more quantitative about this. We can measure how peaked the main lobe of the pattern is, how small the side lobes are, using quantities called directivity and gain. And we'll also introduce radiation efficiency. So the directivity, we go back to the power density, and we take the maximum value, and we divide that by the radiated power over 4 pi r squared. Now, this is a really interesting relationship. On the top, we have watts per meter squared. Power density is always watts per meter squared. On the bottom, we have the total power radiated by the antenna divided by the area of a sphere. Now, that is where the power would go if the antenna were ideal or isotropic. So really what we're saying, directivity is the S of our antenna radiated relative to the S of an isotropic antenna that radiates the same amount of power as our antenna. So we're kind of comparing our antenna to an isotropic antenna. That's a dimensionless quantity called directivity. A lot of times we'll convert that to dB and give it a value in decibels. Next quantity, antennas are lossy in general, so we talk about their radiation efficiency. We take the radiated power and divide it by the transmitted power, the power going into the antenna. So here's the antenna. We have PT going forward on the transmission line. Then I'm going to put the antenna losses in a box, and that would represent the ideal or lossless part of the antenna. And if I integrate the power density, watts per meter squared, I integrate that over a full sphere using double integral s dot r hat r squared sine theta d theta d phi. That is what we mean by total radiated power. That converts watts per meter squared power density multiplied by meter squared in the integral to give me just watts. Okay? Because of the losses in the antenna, the radiated power is less than the power going into the antenna, and radiation efficiency measures that ratio. That will always be 1 or less, 100% or smaller. With radiation efficiency and PT, we can now define the gain. Gain is the same thing as directivity, but we put the PT in the denominator rather than Prad. And then using the above formula, we can say that the gain is the radiation efficiency times the directivity. Now, gain is a little fairer measure of the performance of an antenna because it includes losses. I could have a really directive antenna, but if it had a lot of loss, just a lot of resistance unnecessarily, the gain would be poor. So that's kind of a truth in advertising quantity. And just like directivity, we report that very often in dB. 10 log 10 of the gain is a natural number. Okay, last little idea. We're getting down to the end here. And that is that the radiated power, if we look at the circuit model, is 1/2 I naught. I naught is the power going into our antenna terminals, the transmission line port, and then R rad. Using that, I can write the radiation efficiency as 1/2 I naught squared R rad over 1/2 I naught squared, and then R rad plus R loss. So you can see that the loss and the radiation resistance together determine the radiation efficiency of an antenna. Before we leave this, let me make one more note. What we're talking about with directivity and gain are the maximum values of those quantities, but I could also look at, for example, S as a function of R and theta and phi over P rad over 4 pi r squared, and that would be the directivity pattern. Okay, so sometimes we talk about the directivity pattern, and that concludes our antenna parameters material.